So the very first thing we're going to talk about today is kind of a refresh of literally what we went over last class, but kind of done in a very visual way. So on the first page that you picked up today, the one again that starts with vertical translations, we're remembering that vertical translations are adding numbers or subtracting numbers behind the original function. And today we're going to be focused mainly on that new type of function, the absolute value. So if you look at this graph, let me zoom in. The absolute value of x plus k is going to move the graph up if you literally see plus k. If behind it you see minus k, that means the graph is going to go down. So if you see here, and if you want to highlight the new one, this one right here that's not dashed, the dashed one, the little dotted one, is your parent function every time on these notes. See how that one moved down because we told it to move the parent function down? And specifically it moved down 5 units because it went from the origin to the number -5 on the y-axis. Really pretty simple. That's vertical translations. You add or subtract numbers behind. For the second type of transformation we talked about yesterday, last class, is a reflection over the x-axis. Notice this time there's just a minus sign in front of the absolute value bars. What that will do is it will flip over the graph, making it a frowny face. And I know it's like a upside down V instead of like an actual like sad parabola. Actually looks like a frown, but this one is still sad because we have that negative in the very front. We discussed why last time all of this happens. We also talked about vertical stretches and shrinks. So both of them have the same formula. They're both A's or numbers multiplied in front of the absolute value bars. But if the number is a big number, greater than 1, then the graph is going to get narrower. Okay, that's the word we're going to look for, narrower. So this 2 in the very front of the absolute value bars is a big number. It's bigger than 1. So it's made the graph narrower. If that number we're multiplying in the front is a fraction, like 1/2, 1/3, 1/4, 0.5, if it's between 0 and 1, the graph is going to get wider. And that's why this 1/2 right here in front of the absolute value bars had made the graph wider. We discussed this last time, so this is just putting it all onto nice, pretty visuals for you for your notes. I think this and the next paper that we look over will be the most helpful today. The last thing I want you to write on here, and there's not really room anywhere except for the very, very bottom, is the letters V-O-S. V-O-S. VOS. V-O-S, VOS helps me remember that my vertical transformations, vertical is V, happen outside the parent function, not inside the parent function. We do stuff to the outside of the absolute value bars. And the S tells me that it goes the same direction. If I say plus, it goes plus. If I say minus, it goes minus. If I say big number, it gets narrower. If I say small number, it gets wider. That's the same. That makes sense to me. Big numbers make it bigger. Small numbers make it smaller. So it's either skinny or wide. Okay, on the other hand, we have another piece of paper that instead of working with all of our vertical transformations, we have horizontal transformations. So flip over to that one. Instead of VOS for this one, the acronym we're going to use is HIO. That stands for horizontal transformations inside the parent function, and they go the opposite direction than we think, which means that if we are doing a horizontal translation, when I subtract numbers, it's actually going to go to the right, which is weird because the right direction is my positive numbers on a number line, but subtracting something on the inside makes it go to the right. That's the opposite. It's going to go to the left if I'm adding some numbers inside. So if you see a minus, you say to the right. If you see a plus right here, you say to the left. And that's exactly what's going to happen in this picture. We are adding 5 inside, so that's a horizontal translation, and it goes the opposite direction than plus. which means it goes to the left, minus 5. Moving from the origin to minus 5. We briefly discussed the next transformation last class, but I also told you it wasn't that important because it's kind of weird. You see how this time for a reflection in the y-axis, that negative is multiplied inside. It's not on the outside anymore. When that happens, we're going to be flipping over the y-axis, which is this right here. But that graph lands right on top of itself, going from looking like a V to still looking like a V instead of flipping over. So that one's not very helpful. It looks the same. It doesn't really do anything for this particular type of function. Later on in this class, doing something in the y-axis will look different, but for this function, which has a property called evenness, which you don't need to know, it won't really change anything. Kind of like our parabolas. It doesn't change anything with those either. Now these last two transformations are a little bit confusing. They're called horizontal stretches and shrinks. Their number is no longer multiplied in front of the absolute value bars. It's multiplied on the inside, which makes me know that it is a horizontal transformation. I also know that it's going to go the opposite direction. So this time, you flip the number you're working with. You see how the A is not just a number by itself, it's a denominator? It's the opposite. We flipped it up, called a reciprocal. So it's flipped over. And if that number is a fraction, then it's going to get wider. But that's called a stretch now. So it's the opposite of the vertical versions, which makes it confusing. So if you see a fraction in there, it's no longer making it stretch, making it shrink, it's making it stretch, but it still gets wider. So fractions always get wider, and big numbers are always going to get narrower, but their vocabulary switches. This time, if A is a whole number, like 3, it's still going to get narrower, which is what happened with vertical, but now it's called a shrink. So got to pay attention to these vocabulary words right here. The horizontal transformations are legitimately confusing, okay? So don't stress out too much about them. We do need to know how to use them, but they're just the opposite of the vertical versions because horizontal is inside and opposite. This one got narrower. I forgot to highlight that word. Okay, so what we're going to be working on today is not only recognizing the vocabulary of transformations, but also writing equations occasionally for these transformations. I think that these like 2 pieces of paper that we already wrote on are going to be the most helpful for you, which is why I separated them so you can glue them in your spiral later, like side by side on 2 pieces of paper. I think that's super helpful to see. Okay? But our practice problems are going to go into the next one, the one you can fold in half. Because again, not only do we need to recognize the transformations from a graph and know how to make them do certain things on a graph, we also need to be able to write the parent functions. So we have 3 steps to do that, and right now it feels like a whole lot of steps for not a whole lot of work, but I promise you when we do day 2 and the problems get a little bit more difficult, you're going to want to do these 3 steps every time. So the first step into writing the rule for a transformed function is to do what's called writing the rule or the equation in function notation. Now, what in the world is function notation? Can anybody remember what that is? I spelled that word wrong. Notation. Embarrassing. Okay. Does anyone remember what that is? Function notation? You can say no if nobody remembers. Thank you for your honesty. Yeah, function notation is the stuff that looks like this. Do you remember that? That's called function notation. So we're going to write a lot of those. How do you say that? Does anyone know how to say that? F of x. Fabulous. Yes, f of x. So don't say fx, don't say f times x. It's f of x. What that means is that we're using the function that happens to be named f, and the number that we're plugging in right now is an x. If anything changes about that, we plug in a different number. Or if we're using a different named function, we change the name. Step 2 is to substitute in the parent function. So we're going to substitute or replace the parent function. And then the third step, which sometimes, especially today, we won't really have to do this step. This will be helpful really pretty much next time, is we're going to simplify, again, if we need to. Today, we may not have to simplify very much, but next time we probably will. So we're going to write the rule and function notation, then just plug back in the parent function, which today is going to be absolute value of x, if that's helpful for you to write there. And then we're going to simplify if we need to, because we're writing the equations this time, not just graphing and seeing what happened and talking about vocabulary. We're doing the equation writing. Example 1, f of x equal to x. And we want to translate it down 3 units. One thing I want you to do real fast, there's a typo right here. I want you to add the absolute value bars around that x. This should be an absolute value. My bad. Okay, cool. Now we're on the same page. Okay, so we have f of x equal to absolute value of x, and we want to translate it down 3. Now, if you look at those visual aids I gave you and we wrote on before, how do I move something down 3? Is that an inside or an outside? Outside. Am I going to multiply or add / subtract? Add. Now, what number am I going to add? Ooh, but that will go up. Yeah, minus. We would subtract 3, which is the same thing as adding -3. Like, technically, those are the same things. So here's how we do this. We start by saying the new function, we're going to name it g of x. So I changed the function. And in function notation, I'm going to take the original function, and I'm going to translate it down 3. That's the first step. We wrote the new name. The new name of the function is g. And I'm going to take the original function and move it down 3. That's all I've written on my paper so far. So then I substitute in f of x. F of x is equal to absolute value of x. So instead of writing f of x, I'm going to put absolute value of x right here. I've replaced the parent function, and I don't have to simplify anything. G of x equal to absolute value of x minus 3 would be a vertical translation down of the parent function. It will have scooted the graph down 3 units. Okay. If it bothers you that there's just like an equal sign with nothing equal to it, you can rewrite the g of x right here, because we're saying g of x is equal to absolute value of x minus 3. So if that feels better to you, not just have a random equal sign on your paper, that's what's happening. We didn't need to simplify anything, so we didn't have to do step 3, and that's the total gist of today. Let's try the second example. It says we want to translate the absolute value function 2 units left. Is left going to be an inside or an outside transformation? Inside. Now to move to the left, I'm going to be adding some number or subtracting some number. Adding 2. So I'm going to take the original parent function, f of x, but on the inside, I'm going to say x and add 2. I think you're on the right track. Yeah, so once we do this, now we say g of x, and we substitute back in the original parent function. But this time, does the plus 2 go on the outside? No, we said it should go on the inside, so it goes inside those bars, because this is telling me, rewrite the original function, but this time, instead of writing x, I want you to put this in its place. So I put all of x plus 2, bloop, right there. Yep. Again, it seems like that first step we don't need to do. And you're right, in today with these simple examples, it's really easy to go from where we started to where we finished. But I promise you when we get to the more complicated examples next class, you're going to want to follow these 3 steps. Cool. So we know how to vertically translate something. We know how to horizontally translate something. Let's go to a few more examples of some of the other little bit more complicated things to do. The difference between vertical and horizontal is the direction in the words. So like down is a vertical direction and left is a horizontal direction. If I drew arrows those directions, I'm going vertical and then horizontal. To remember which one goes inside and outside, all you need to remember is Voss and Hayo. Voss says that vertical transformations are outside, so that's my vertical transformation, has to go on the outside, and it's the same direction, down is down. The other one says my horizontal transformations go inside, and they're the opposite, so left should be a plus. So Voss and Hayo are going to be your acronyms to help remember if it goes inside or outside. Thank you for that question. I love questions. Okay, now if we look on the inside, the next thing that we are going to want to do is reflect the absolute value function in the x-axis. What do I do to reflect something in the x-axis? Well, yes, but what do I do to the equation? Ooh, and if we don't know, look at those two papers we started with today. It says reflection in the x-axis. What did I change there?
Flip over the x-axis.
Yes.
Negative.
The negative, and where is the negative?
In the inside.
It's on the inside?
Yeah.
Outside. Oh, the negative's on the outside.
The negative's on the outside. To reflect in the x-axis, the negative's going to be on the outside. This one, it's so important for this one in particular that you put it on the outside and then you say f of x before you try to do the parent function stuff, especially for next class. So now if I actually simplify this or replace f of x with the negative x, now I have g of x, the new function, equal to negative absolute value of x. The negative is on the outside. Again, feels like you can go from the beginning to the end today. Yes, you probably can, but next time it will be helpful to see that in-between step. Next one we want to do is reflect it in the y-axis. How do I reflect something in the y-axis? Put what on the inside? Fabulous. We put the negative x on the inside. So this time I say that g of x is going to be equal to f of x if I put a negative on the inside. So anywhere in my original function that there was an x, I'm going to replace with negative x. So if I write the new function, g of x is going to be equal to the absolute value of negative x. Boom. That will reflect it in the y-axis, which doesn't visually change the graph at all. Okay, example 5, we want to vertically stretch something by 2. Vertical stretches, are those inside or outside?
Outside.
Outside, very good. Vertical is definitely going to be outside, remember, because of Voss. And a stretch means that I'm going to multiply the number instead of add and subtract it. And multiplication always goes in the front, so when I start to write this, I'm going to say g of x is equal to 2 times f of x, because I've multiplied it in front. Remember, two things just smushed next to each other are multiplied, so we know those are multiplied together. Okay, then we can replace the f of x with an absolute value of x. Cool. So that is a vertical stretch. Again, we're just going to continue with this pattern every single time. But we have a little bit more explanation here on those horizontal transformations because they're a little crazy. So let's talk for a second again about horizontal stretches and shrinks. So horizontal shrink, the formula is f of ax. It moves the graph towards the y-axis, and the fraction is less than 1. Remember, this one gets narrower. A horizontal stretch, on the other hand, remember that was shrink. A horizontal stretch, same formula, but it moves it away from the y-axis, which again means wider. And this time the fraction is bigger than 1. Because these are horizontal and inside, the number appears opposite, or the reciprocal in the equation. So the opposite number we use, it goes the opposite direction than we think, because stretches get wider and shrinks get narrower, which is opposite of vertical. So horizontal, inside, opposite. So here's how we attack these. If we want to write the absolute value of x with a horizontal shrink by 1/3, first things first, the number they gave you for a is 1/3, which means instead of 1/3 when you plug it in, you're going to flip-flop it, and the a that you're going to use is what? Not 1/3, but 3/1, which I can just write as 3. Whew, okay, we did the opposite because it's horizontal. So we start writing this. We would say g of x is equal to f of no longer just regular x, but that flipped number 3. It's going to horizontally shrink it. I have to flip the number. So it goes inside the parentheses. It also goes inside the absolute value bars when I translate that into the function without function notation. So horizontal's opposite. Whatever number they give you, you have to flip over. That's the number you're going to multiply by, which makes these, again, a little bit more confusing. But it's a simple thing. Just flip it over. We just have to remember to flip it over. So if we wanted to horizontally stretch something by 4, they gave me that the number is 4, so what number am I going to use?
4.
I think I heard it. 1/4. Yeah, you got to flip that number. Yeah, there's no denominator showing, but every whole number has a denominator of 1. Okay, so if we do what we've been doing this whole time, we're going to say the new function called g is just the regular function, except that I'm going to plug in 1/4 x instead of x, because I'm horizontally stretching it. Exactly the same. Yeah, whatever you've written inside the parentheses in function notation, you plug inside the absolute value bars. So if we graphed that, that would be a horizontal stretch. It would get wider. We need to be very comfortable with writing the equations, but before we can really do that, we have to remember what this vocabulary is. So what we're going to practice today is a little bit back towards the graphs, like you wrote down on your first 2 pieces of paper. But I want us to not forget about the equations, because next time we're going to be writing equations, they're just going to be a bit more complicated. We'll start combining things together, doing 2 or 3 at the same time and writing the equation there.